Hello and welcome to Fact-Based Living. I'm your host Newton, and today I want to talk about something that I've seen some confusion over in the past couple of days on a couple of videos. So I wanted to kind of tell you how I use this particular term and where I'm coming from on it, and where I think a lot of the scientific community is coming from on it. And the word that we're using is precision. So let me explain kind of how precision works. So here is a simple part that I knocked up in SolidWorks. It's about as simple as you can get. It's 4 sides, 4 holes, and that's about it. And if I were to make a drawing of this part and send it off to a machine shop, they would be able to replicate this part and manufacture it in such a way that I could use it in multiple assemblies and it would always fit. Now, one thing you have to understand about any process, any measurement, any machining, is that you can never make any two parts perfectly identical. In fact, you can't make any two parts perfect to the drawing that is provided by the engineer. It's simply impossible to make things dead on every single time, if at all. So the way we get around this in manufacturing is we build in a little bit of wiggle room into the process so that the machinist has a certain amount of error that's allowed in order to make the part still usable but machinable in a reasonable amount of time with a reasonable amount of equipment. Now let me show you the drawing for this part so I can explain kind of how that works. I'm going to go over here to the drawing. And here in this corner we have one of the 4 machined holes with a dimension put on it. In this case, this dimension up here that I'm now highlighting says that it is a diameter, which is what this symbol means, of 0.551. So that's telling you what size hole, what diameter hole you need to machine here. Now, the precision of this measurement is to 1,000th of an inch, 0.551. And using that, the machinist could choose the appropriate drill bit or milling profile in order to make a hole that is 0.551 in diameter. But the problem is he can't guarantee that every single hole he makes is going to be exactly 0.551. So how do we get around this in manufacturing? Well, the way we do this is we introduce a thing called a tolerance. And basically a tolerance provides some wiggle room for errors to occur in. So let's take a look at another one of these holes, but with a tolerance. So here you have a hole that is the same diameter, 0.551, but now it has a note at the end of it stating what the tolerance of the hole is. And so the way to read this is make a hole that is a diameter of 0.551 plus 0.003 or minus 0.00. So what that means is you can make the hole 0.551, it can be bigger by 0.003, but it can be no smaller than 0.551. Because if it was any smaller, you might not be able to fit the bolt or the peg or whatever it is that's supposed to go in here. So the tolerance on this, or the room given for error, is 0.003. So that means that your hole could be anywhere from 0.551 all the way up to 0.554 in diameter. So there's a bit of wiggle room built in there. Now, if you were to measure this hole, say this machine is, or this particular part is machined and you have it and you're checking with a pair of calipers, your calipers also have a bit of wiggle room built into them. So your calipers that you're measuring this hole with might have a precision of 0.001, so that means it can read to an accuracy of 1,000th of an inch. But the accuracy of that measurement might be plus or minus 0.002. So that means that it's only accurate while it has a resolution that goes all the way down to 1,000th of an inch, it has an inaccuracy potentially of 2/1,000ths of an inch. Now, the way to sort of visualize that in your head is imagine a ruler that only has tick marks on the 1/8 of an inch, and you're trying to measure a long plank of wood with it. So if the end of the plank of wood ends up in between an 1/8 of an inch tick mark, then the accuracy is limited to only where those tick marks are. Any measurement that falls between the tick marks is going to be in that error range, plus or minus an 1/8. And that's really all we're saying here, is plus or minus a small amount of deviation from it. Now, in science and physics, a lot of times we simplify our formulas to make them easier to use. So, for example, the acceleration of an object falling is usually said to be 9.81 meters per second squared. In actuality, we've measured it, and it goes out to like 16, 17 decimal places wherever we're at currently. We keep refining that measurement. And of course, that measurement varies based on how much ground is beneath you. So it's going to be slightly different on top of a mountain versus like right on a beach at sea level, because there's going to be a difference in mass between you and the ground. So that precision of only taking out the 2 decimal places is good enough for most things that you need to do. But if you need be, you can take it out to a few more decimal places. So that's one example of where we use the decimal precision to determine kind of how accurate we're taking our measurement. The other thing to understand is that with any sort of measurement, there's always those error bars, the tolerance of the measurement, so to speak, that come into play. Because you can only measure something so accurately, and there's going to be a little bit of fuzziness right at the resolution of your measurement. So everything always has a plus or minus tolerance value on the measurement at its minimum scale. So that being said, what I wanted to talk about was a couple of people that were a little bit confused about parallel light rays. Now, in science we say that light coming from the sun comes in parallel, and if you look at the geometry of it, this kind of doesn't really make any sense. So I've kind of knocked up a little bit of a model here. SolidWorks is being a little bit finicky. I would have liked to have had this point like right at the surface, but here's our model of the sun versus the Earth, and we've got the equivalent of 93 million miles in between the sun and the Earth. That's what this is. I had to make this 1/10,000th scale because SolidWorks doesn't like numbers above 300,000. So I had to kind of scale things down a little bit. But everything here is 1/10,000th scale, and the scale doesn't really matter when you're dealing with things like angles and stuff, because the angles are always going to work out the same. So anyway, what I did here was I drew a couple of tangent lines right at the poles. And what a tangent line means is it's basically parallel to the circle at the point where it intersects the circle. So you can see this parallel line is coming out here, and there's a parallel line down here. And the reason why I drew this was to illustrate a point about light coming off of an object. So in order for that light to escape the surface of this circle and actually be observed by something, it has to be emitted in an outward direction. And if the angle it takes is anything less than this tangent line from this point, it's actually going to run right back into the surface of the sun, which means that that little photon of light is not going to be observed by anybody. So I don't know if you want to call it a maximum or a minimum angle that a photon of light could leave the pole and actually come out and be observed by something is this 90-degree line right here. Anything above this 90-degree line is a spot where a photon could be released and observed. Anything below it is where one wouldn't. So I decided to go ahead and draw in another point fairly close to the pole just to, keep it consistent, and show a tangent light ray taking like the minimum angle that it can possibly take and coming across and striking the surface of the Earth. So this very sharp, acute angle here. So already we kind of see a problem with this illustration, that this is obviously not coming in parallel to this one. Both of these are leaving, a similar point on the surface of the sun. They're coming in at a very, acute angle. And I think this is the picture that a lot of people have in their head when they're picturing light rays coming off of the sun, because trying to represent the true scale of the solar system on, anything 2D is really difficult to do. The objects are very, 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 very far spaced apart, and relative to the distances in between, they're actually pretty tiny, even when you're talking about something like the sun. And so our understanding in our heads, our intuitive understanding of the scale of these objects, is horribly, horribly skewed. So what I'm going to do here is I'm going to keep this distance the same. And yeah, I know it's slightly off because it's going to the core instead of the surface. And I'm not actually sure if the measurement is from the core of the sun to the core of the Earth, but it's close enough for our purposes here to kind of see what the angles look like. And so the first thing I want to do is I want to take a measurement in this current state, and I want to see what that angle is. So I'm going to come up and I'm going to grab my Smart Dimension tool, and I'm going to take an angular measurement from our light ray to this vertical line. And you can see, right there, it's 69.62 degrees. And the angle between two similar, I hate when SolidWorks does this. It won't let me do two dimensions at the same time. Yeah, see, there's that silly number rounding thing. Come on, SolidWorks. There we go. Delete that. Oh, come on, really? This is the maddening thing sometimes with SolidWorks. Like, it won't let you just grab the thing that you want and delete it. Actually, I can probably do a Control-Z. There we go. I gotta be smarter than the computer. So, let's take a angular measurement between our two light rays just to see what that is. So we had 69 degrees from vertical, and we've got about 40 degrees difference here, right? But granted, this is at the scale of stuff that we're all kind of intuitively picturing in our heads. This is not the scale of the objects themselves. While this distance may be to scale, the size of these two bodies is grossly out of whack. So I'm going to go ahead and delete that dimension out, and I'm going to adjust the scale of the bodies. So I know that the size of the Earth in 1/10,000th scale is going to be 0.7917. And that shrunk it down to almost non-existent. There we go. So, just to prove to you that the circle is still there, there's the circle. I'm not going to subject you to my mouse clicking like crazy. So, now our Earth is to scale, but you see there's still a big giant angle here, and that's because our sun is not quite to scale. So, to get our sun into scale, I did the math on it earlier. You take 864,337, divide it into 1/10,000 scale, and you get 86.4337. I'm just going to round this off to 86.43. So I'm going to grab my sun, make it 86.43. And hit enter. And now our scale is a lot closer to what it would be in real life. So here's our sun. There's our same 2 points. They may have moved in a little bit in angular size because I didn't lock these with an angle, but really not that much. And now what I want to do is I want to take this angular measurement from here to here, just like we did before, when it was quite an acute angle. I'll put in a smart dimension, and we'll measure from there to there. And we end up with 89.94869534 degrees. So basically 5/100ths of a degree from vertical. Very, 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 very tiny angle. And mind you, this is taking the most acute path that it could from, basically from the very top pole of the sun here all the way down to the equator of the Earth, essentially. And it's only making 89.95 degrees. And I'm going to delete that out. And I'm going to do, see if it'll let me. It may not let me. I may assume that these are parallel. And okay, so it actually did measure an angle, and the angular difference between these two light beams is not even 0.10260932 degrees. So 1/10 of a degree. And mind you, this is not quite as accurate as, real-world measurements because I'm doing this in CAD and kind of fumbling around. But you can see here that, I lost it. I'm going to have to bring it back with this. But you can see, we know that these two lines up here, these two dashed lines, are exactly parallel. And if we look at our line here, that's our light ray that we know is off by about 1/10 of a degree, you can't really see a difference. For all intents and purposes, these are parallel to each other. And that's actually what scientists mean when they talk about parallel light rays coming from the sun. It's not that they're actually perfectly parallel, but they're so very, very, very close to parallel that it's almost a distinction without a difference. It's such a tiny angle, in fact, that until the advent of modern electronics and stuff, it was almost impossible to measure these tiny, tiny, tiny angles. And the angles of the light rays coming off the sun are actually a smaller angle than this, because like I said, SolidWorks is doing some rounding and some funky stuff with the circular math, because it's not designed to do it to that level of precision. But I hope that kind of clears up some of the misunderstanding that a lot of times, especially in science, when we say something is essentially parallel, or let's flip that around, when we say that something is parallel to something else, it may mean that it's parallel to such a degree that we can't measure it, so you may as well treat it as if it was perfectly parallel. But in this case, we know it's not perfectly parallel. We've known this for a long time. But it's so close to perfectly parallel. It's so within those error bars in our measurement that it doesn't matter. Like, it really doesn't matter for most things. So I hope that kind of clears up how precision works and how the parallel light rays thing is actually parallel, because it seems to be something that comes up over and over and over and over again. And it's like, look, we don't mean that it's perfectly parallel, we just mean it's parallel enough that you may as well treat it as if it was, to simplify the math. Because any tiny little bit of error you're going to introduce by not taking it in, perfect, 30 decimal places of precision, isn't going to matter to your calculation. So I hope that kind of clears that up. I will be having another episode out, like a full normal episode out this weekend. I'm kind of in the process of wrapping that up. But I wanted to get this one out because I figured it was kind of an easy one to demonstrate and show. And I hope that clears some things up for some people. That's it for this episode of Fact-Based Living. If you like this video, go ahead and give me a like and subscribe below. If you have any ideas for something you would like to see illustrated or explained in a visual way, just drop me an email at factbasedliving@gmail.com. That's factbasedliving, all smushed together, @gmail.com. Alright, I'll see you later in the week for another video. Bye.